trying to get you to think of in this case is sometimes you do a hell of a lot of background literature research in order to come up with a hypothesis. Because hypotheses, good ones, are justified. Justified means it's not a shot in the dark, right? And then if you go and make an argument for what kinds of things may go into accounting for a substantial amount of solute inside of a potato cell, then you could predict, if I go and take these potato slices and I put them in increasing amounts of an osmotically active solute and I measure the percent change in the mass and graph that result, wherever I get my x-intercept, that is going to experimentally determine what the osmotically active solute concentration is. And you could match up what you get from your graph to and some values that you were speculating about in the hypothesis. Right? So you could go and make a hypothesis about an OAS concentration without predicting a specific osmotically active solute concentration. You do with the ELISA. All right? Does this patient have smallpox? Right? Well, because of the sensitivity of an antibody, if a patient has a specific antigen I'm trying to identify, and if I have this antibody that recognizes this antigen, I could design a test where I'm using this primary antibody to recognize this antigen I'm trying to detect that's associated with the smallpox disorder, and use a secondary antibody to recognize that. I should be able to detect the presence or absence of a particular sample. And then in the ELISA, I will have this color change for this being positive control sample. If I have a patient that's infected, I will have this specific outcome in the test strip. So the hypotheses are going to be a statement that attempts to explain a question. Okay? The prediction is going to be based on a specific experiment that is going to be testing that hypothesis. So your challenge is to go back. Got a whole litany of examples from lecture 2. Right? Here's a question, here's a hypothesis, what would be the prediction for it? Okay? Another one that comes to mind is the cell-cell adhesions. They took the sponges, disintegrated the sponges, put them back together. Right? Your book talks about the question. Gives you the hypothesis. Right? Doesn't really do the prediction step, but you could go and add in what would be the prediction step. Now, let me just go and read off a couple of great answers for the quiz question, depending upon the version of the quiz you got, that ask for the difference between a hypothesis and a theory. All right, so this one says, a hypothesis is a proposed answer to a question. The hypothesis is tested and the results supported. In time, it may become a theory by itself or grouped in a set of connected hypotheses. The difference is time and supporting data. That's a perfectly good answer to that question. Here's another one. Again, it's not like you're trying to match the magical combination of words, right? I'm not trying to get you to do that because there's multiple right ways of phrasing an answer. Here's a very different one, but it's equally correct and equally great. A hypothesis is an attempt to answer a question on the natural world. A theory is a model of explanation of the natural world supported by observation, hypothesizing, and testing. A theory has more time invested to back up itself than a hypothesis, and a theory has more explanations than support. Right? They're saying something in a very different way, but they're saying the same thing. Right? So that's all I'm trying to get you to realize. You can say the same thing in multiple different ways. You just got to get that point across.
Yeah, just a question on diffusion and osmosis. Can we view diffusion as can we view osmosis as diffusion of water? Is that what you look at it?
Not only can you should.
Okay.
Yes. It is a special case of diffusion of water, process electrically permeable.
Isn't there another part to that though too? From high free water to low free water?
That's the definition of it. Yep. From high free water to low free water. Or if you don't like that free water part from low concentration of solute to high concentration of solute, or from hypotonic environment to hypertonic environment. All of those are getting across the same thing.
What is the difference between a sedentary membrane and a subjective?
Nothing. Who you talk to and what you read, they are exactly the same thing. Don't blame me. So many words mean exactly the same thing, right? It's you ever listen to people who study words from different languages and different cultures, right? You can kind of get an idea sociologically what a particular culture's value by how many words they have for it. Like first time I ever heard of this, like Eskimos have like 30 words to describe snow. Like we have snow, right? And then if you look at it in English, we've got like 30 words to describe money. Right? Think of how many words mean money. Right? So I guess in science we have some number of words that kind of rank qualify our importance. Yeah.
Relative mobility and molecular weight, are they interchangeable?
What was the first one?
Relative mobility and molecular weight, are they
Those are not interchangeable terms.
not interchangeable, I meant inversely related.
Yes. So inversely related, inversely proportional, just simply means that one value goes up, the other value goes down. Right? So go back to lab 2. Okay? And it's under the section of correlations or relationships in data. So if I were to go and have a relationship like this, right, where I have x and y, that is a negative correlation. As x increases, y is decreasing. That's an inversely proportional relationship, or a negative correlation, right? As relative mobility increases, my molecular weight decreases. Smaller things move easier through the gel. Okay? So if this is going to be diffusion rate, and this is going to be diameter, size, if you will, of the molecule, it's the same relationship. Right? The size of a molecule gets bigger, it doesn't move as fast. Brownian motion. Inversely proportional. Negative correlation. Alright, now if I were to go, leave that there. Now if I have this, if those two variables are scaling together, as one increases, the other increases. So this could be diffusion rate still. But now maybe this is going to be temperature. When temperature increases, diffusion rate increases. So those are directly proportional, or that's a positive correlation. Okay.
Why didn't we use the analog graph paper to graph the molecular weight again?
Why did you?
Yeah.
Because you said didn't use.
Oh, did.
Why did you use it? So the reason for that is because the range for the relative mobility was just between 0 and 1.8. Okay? The range for the molecular weights are going to be gargantuan. Okay? It's going to be from a few 100,000 Daltons down to a few tens of thousands of Daltons. And if you were to graph that on a linear scale, it would be so compressed you'd actually get a curve. Okay? And so in order to linearize that standard curve and get a straight line for your best fit line, basically just do it semi-log paper. That's the easiest way of doing it. I mean, you could do it on a linear scale if you took a logarithm of the molecular weight and graphed the logarithm of the molecular weight, but then that just becomes more cumbersome actually.